So last class of the week, we will discuss today the FKG inequality. So, but before we do this, I want to discuss some points that I only talked yesterday about something that I call the DLR equations. And first, a reminder. Well, I said that by the proof of that property that the magnetization beta h plus increases with the size of the finite set, or better, during the proof where we assume that A is in psi lambda 1, psi lambda 2, a finite subset of the D. We derived the following expression for the expectation of sigma A in the larger box. We did something. We did a little bit of an algebraic manipulation with this quantity, with the definition of this expectation value, and we arrived at the following expression for this mean, for the expectation value. We got that this expectation value is equal to the expectation value of another function that turns out it can also be described in terms of a mean of a local Gibbs measure, where this function sigma A lambda 1 beta h, this is a function. It's a function on the whole configuration space, where we get where for each boundary condition we associate the mean, the expectation value of sigma A lambda 1 beta h with boundary condition omega. Okay, and this I called something like the DLR equations. Okay, and I also said, actually, Kelvin draw our attention to the point that A needs to be inside here. Okay, but you can also make some manipulations and drop this hypothesis for this to hold. And also, you don't need to use the plus boundary conditions. So show exercise, show that this equation right here holds for any local function. local function and any boundary condition instead of the plus boundary condition. Any boundary condition. Any boundary condition. So, of course, what happens here is that for finite range Ising models, this will also be a local function, and this is important. This function will be local only when the system is finite range. But if it is long range, then you can approximate this function by local functions. So it is a limit of local functions in the general long range case. So you can understand this exactly as an integration of something. Okay, so that's of a continuous function, local function. So okay, and what nice property this gives us is something that we call the Markov property. The Markov property. That is the following. Well, first, if P is a probability, and B is some event with PB positive, right? We can write the conditional probability as being the probability of A intersected with B normalized by the probability of B. Okay? And the Markov property is a property that the local Gibbs measure satisfies, that is related to these conditional probabilities. But when you condition your probability to cylinder events, okay? So first consider, remember the cylinder event. Let's say for any lambda and lambda prime, the lambda prime contained inside lambda, a finite set of ZD. Remember that the cylinder event for a configuration between lambda and lambda prime was defined as being all the configurations here, all the configurations omega, such that omega x equals to sigma x exactly when x is inside lambda minus lambda prime. Okay? And a nice property that these cylinders have is that they constitute a decomposition of the identity in the following sense. If I get this function right here, this function that gives me 1 for any configuration, then I can write this function as being the sum over all the characteristics over the cylinders here, where this configuration varies over all the configurations, okay? So yeah, this is interesting. So let us see what happens to the local, to some local Gibbs measure when I try to condition the probability by some event, So what happens is the following. If I have this probability of some event A, and then let us see what happens to this, and then I intersect it by some cylinder. Okay, this is the same as if I calculate the mean of A times 1 times the cylinder, event, lambda beta h for any configuration here. And if I show, notice that the characteristics of cylinder events are local functions. So if I use, well, let us assume now that A is also an event such that 1 over A is local. So A is an event such that the characteristic is local, because I asked you to show in the exercise that this holds for local functions. So let us stay on this case. So then get 1 over A times 1 over C lambda minus lambda minus lambda prime in lambda prime lambda, and this is a function over here. So what happens now? So remember when we defined the integration over any local function, when we did the extension of the measure to the whole configuration space, we defined for any local function we defined the following. We defined that for any local function f, we defined this mean with respect to some boundary condition, lambda prime beta h, as being 1 over z, the partition function, beta h, and then omega times the sum over all the configurations inside here, omega prime lambda prime omega, times the function calculated in this configuration right here. Everyone remembers what this means. This is the concatenation of two configurations, okay? Times the exponential weight right here. Sigma. It also depends on beta and h. Sigma. Okay, so notice that something really nice happens when I happen to when I have lucky, and this function right here, when I'm lucky, and this function right here doesn't have the support, when the support of f is not inside, so is disjoint with lambda prime. So it's not contained inside lambda prime, okay? So it's outside lambda prime. So what happens that since this function is local, this means that this function over here, it doesn't depend when I change the configuration sigma inside lambda prime. So all of these numbers here are actually equal, okay? And they can depend on the boundary condition because I don't know where the support is, okay? But they do not depend of what happens inside the lambda prime. So then there exists a number, let's say f tilde omega lambda c, okay, such that f c prime lambda prime c, lambda prime c, they are all equal to the same constant, lambda prime c. So this actually factors out, okay? And then I have only the partition when this term right here goes outside the integral here, or the sum, then I will only have the sum over all configurations of the Gibbs weight right here. But this is exactly the partition function, okay? So what happens is that f omega lambda beta h lambda prime will be equal to a constant, to that constant here. It can still depend on the boundary condition, okay? It can still depend on the boundary condition, but doesn't depend on what happens inside the box. So, and notice that if I had a product with any local function g, then this a similar property would still hold. What we would get is that the product of both of the expectation value of the product would be only f tilde omega lambda prime c times the expectation value g here, like this. So this is a general condition for that happens every time the support of the function is outside the set that the Gibbs measure lives on. So this is exactly what is happening in this situation right here, okay? Because, okay, we said that this function is local, we are supposing this. But this function over here, the cylinder set for a given configuration, living in lambda minus lambda prime, its support lives outside lambda prime. Its support is exactly lambda minus lambda prime. So this will factor out inside the mean. And this will give me C epsilon lambda prime times 1 over a, this as a function, lambda prime beta h, and here I have omega lambda beta h. Okay, so what happens now is the following. Okay, I just erased it from the board. So remember the function that associates this a boundary condition to something. For any local function, I can define this. So remember this, and we can ask the question as let us think that we are in the short range case right now. So this will be also a local function, and then we can ask where the support of this function lives. Okay, where the support of this function lives. So similarly, this is the question: what kind of configurations I really see when I choose a boundary condition? Okay, and if you open the definition of this mean right here, you will see that you are integrating over all the sites inside lambda prime. So what this means is that whatever is the support of this function, again, thinking that this is a short range Ising model, so whatever is the support of this function, it must live outside lambda prime. Okay? Again, if you write the expression, you will see that this is 1 over the partition function, lambda beta h, omega times the sum overall here f sigma omega lambda everything is lambda prime minus beta h lambda sigma. There is a beta h over here. So as you can see, the only information that I use to write this expression is what happens outside the box lambda prime. Okay, and the Hamiltonian function also will change because to define this, I only use the information of what happens outside lambda prime. So this is actually a function that only whose support is outside lambda prime. Is the support is outside lambda prime. Okay, so what happens to this expression right here? Let us write this. Let us write that down. So what I have is that expression over there. Let me just mark. Oh, I already used the star, so it will be triangle. So what is triangle? Triangle is actually will be equal to 1 over z lambda beta h eta times the sum, okay, overall the configurations inside lambda eta of the characteristic of the cylinder set omega times what is inside, and what is inside is 1 over a, is the mean of this 1 over a. Well, remember that the mean of the characteristic function, for any boundary condition is just this, right? So this is mu with some boundary condition omega and lambda prime beta h calculated at a times the exponential lambda beta h omega. Okay? So what happens now? I know that the support of this function as a function of omega by our previous discussion need to be outside lambda prime. But notice that since we have a boundary condition outside lambda, so lambda is fixed, this function right here will only depend to what happens between lambda prime and lambda. This is the only degree of freedom that I have for this function to vary. So, but since I'm multiplying this by the cylinder set, okay, the cylinder set will be 1 only when omega matches with sigma lambda prime minus lambda, or better, when omega matches with sigma inside lambda prime minus lambda. So this implies that in this product over here, this function over here will be fixed, okay? And it will be fixed and will be always equal to mu sigma lambda prime beta h a. But then this comes out of the sum, and then I have mu sigma lambda prime beta h times a times what? Times 1 over the partition function, the sum omega lambda eta, the characteristic of the cylinder omega e minus h lambda beta h eta omega. I'm summing over omega. Oh, also, outside, I will write this over here, lambda prime minus lambda eta. I will write this over here because what happens is that the configuration outside lambda is always eta. So you must remember this, okay? And then what is this? This will be exactly the expectation of the cylinder set in lambda. Of the cylinder set in lambda. Eta beta h. So what we did actually proved now is that the local Gibbs measures have a nice way to relate the conditional probability with respect to cylinders, because we started with this, okay? And then we got that this will be equal to something that is also a local Gibbs measure, but now depending on the boundary condition that you started concatenated with the boundary condition given by the cylinder, times the probability of the cylinder, H, the cylinder. Okay? Okay, this will be important for us to prove the FKG inequality. So yesterday we introduced a new kind of function of special functions, of local functions, that have some nice property related to an order on the configuration space. So remember that the spin, the state space, it's just -1 and +1, so you have an order here. -1 is less than 1. And then you can have the order on this set induces a partial order on the whole configuration space. Remember, the configuration space, just the product, the power ZD, okay? Given by two configurations inside here are said to be related, and one is less than the other, if and only if sigma x is less than or equal to omega x for any x in ZD. You can try to think a little bit on this order to see why this is a partial order. So to be partial, you are not allowed to compare every two configurations. So think in an example with, I don't know, two spins. So a function is increasing or non-decreasing. A function a local function is increasing, or better, non-decreasing, if a local function f is if and only if every time I have two configurations, one is larger than the other with respect to this order that I just introduced, then f calculated at the configuration sigma and f the configuration calculated at omega. Okay? And notice that we have some examples of functions that are non-decreasing. So the examples were sigma x, for instance. This is an exercise actually to show that this is non-decreasing. The NA, and remember NA is this function right here. NA calculated at omega is given by this expression right here, where A is a finite subset of ZD. Every single one of these functions are non-decreasing. And what is interesting is that I showed you a couple classes ago, that these functions can also be used to write any local function. So any local function is also a linear combination of non-decreasing functions. So as an alternative to study convergence of the Gibbs measures, you can, instead of looking to what happens to the sigma a's that we did during this week, proving correlation inequalities related to sigma a, you can study correlation inequalities related to non-increasing functions and the non-decreasing functions. So the most important inequality of this kind is the FKG inequality. So what is the FKG inequality? FKG inequality. The FKG says the following. Given F and G non-decreasing local functions, JXY, the couplings of the Ising model, ferromagnetic, so positive numbers, or better, non-negative. They can be zero, non-negative numbers. Okay, and HX, a collection of real numbers, then it holds the following inequality. If I take the product of F and J and I calculate this property right here, I will still write H, but I'm denoting this H is actually the collection of all these fields, these magnetic fields. The product, the expectation value of the product will always be equal to the product of the expectations. So FG beta H. So this means that the correlation between F and G when F and G are non-decreasing is always positive. The correlation between those two functions will always be positive, and this holds actually for any boundary condition. Any boundary condition. So just to compare, so for you to remember what we saw and connect to what happens in the case of FKG. The Griffiths inequalities, the GKS inequalities, they apply to any system with multi-body interactions, but they need to be positive. Every single one of the couplings need to be positive, but they can have many body interactions. But they apply only for since the couplings need to be positive. The fields, the magnetic fields, in special the magnetic fields, need also to be positive. They can be not constant, okay, but positive. But they need to be positive. And this is the first difference with the FKG. Now the fields. Oh yeah, no negative. Yeah, exactly, no negative. Thank you. So they need to be no negative. But in this case, they can also be negative. Okay. In this case, they can also be negative. And Another difference is that in the Griffiths case, we had that we proved we could put many body interactions. Now we are only allowing these two body interactions here, and also different from the Griffiths case, we only had empty boundary conditions or plus boundary conditions. In this case, we can have any kind of boundary condition. So in many cases, it's better to use the FKG inequality to study the measures. Okay? Okay. So let us prove this inequality. The proof will be an induction. The proof will be an induction. An induction on the size of the box. On the size of lambda, okay? On the size of the lambda. So we start with just 1 point, okay? So what is the expectation value of the product Fg with an arbitrary boundary condition, lambda, beta, h, okay? In this case, I will just write x here to denote. I will not write the brackets, but this means that this is the mean only living on x. So this is the sum over the spin sigma x being -1 or +1 f sigma x, and I complete the configuration with omega, g sigma x omega x here, and then the exponential of -h x omega beta h calculated at sigma x. Of course, everything divided by the partition function over this set, the set of just 1 point. Okay, but notice I will do some trick here that will not be clear now why I'm doing this, but I promise you that will make sense in just a couple of minutes. I can rewrite the same expression here, but change the name of the variable, okay? Theta x, omega x here, j omega x outside, And then the same, but now depending on eta x. So I have just the same thing over here. Let's see what happens with this product. Omega x beta h times g x beta h omega, and then I will have 1 over the partition function squared, okay, 1 over the partition function squared beta h here. Oh, sorry, there is an x here, times the sum. And now I will be clever, and I will write this as being the sum over these two variables here, sigma x, eta x, inside minus 1 plus 1 of what? F sigma x omega x lambda c g sigma, well, 1 sigma and 1 will be eta times what? Times the exponential of minus h x omega sigma x minus the exponential x, oh sorry, there is a beta h here, beta h here, eta x omega here, okay? And now I can do the same trick, but now just changing the name of the variables, sigma x, so this will be equal to z squared, z omega squared, so z omega beta h squared times the sum sigma x beta x inside here minus 1 plus 1 f eta x omega x here g sigma x omega x c the exponential of x beta h omega sigma x minus h x beta h omega eta x. So this doesn't change, this part doesn't change, I just changed the variables right here, okay? So now you see, I want to study the difference between this and this one. So there is a first problem related to the fact that here I have z squared, and here I have only z. I have only z. But this poses no difficulty because I can add a term of the Hamiltonian. I can add a term right there and write the sum over that product over here, this product right here, so yeah, let me write everything down. So F sigma x omega G sigma x omega times the exponential x beta h summing over omega here, and I summing here over sigma. But I can add another variable, okay, summing over the exponential, over this exponential. Depending on eta x. Okay? But what is the price that I pay for adding this sum? I must divide by the partition function. I must divide by the partition function. Sigma x, beta x. And since I already have another partition function here, then I have this squared. And I can do the same thing to this sum over here. This sum over here, but changing the variables. So in the end, to calculate the sum, the difference here, I can show it's the same as showing that 2 times this is still positive. And then I will sum these 2 copies and sum these 2 copies with the different variables. And then I will have after some algebraic manipulation, you can check that you will have Fg, the expectation value with respect to omega. I'm using omega, right? X beta h minus Fg omega x beta h g omega beta h omega. I will have that this will be 1 over the partition function squared, summing over both of these variables here, minus 1 plus 1, times what? Times f sigma x minus f eta x, g sigma x minus g eta x, times the exponential term. Okay. I will put an omega here, just for you to remember that f omega sigma x is just f sigma x omega x. Okay, and the same for g. For g omega. But what happens now is the following. Remember that both of these functions are assumed to be non-decreasing. So if sigma x is less than this function right here, so this will have the same sign as this one. So the product will always be positive. So this is larger than 0. And notice that this trick will also work for any probability measure, okay? For any probability measure in any box. But if you integrate functions that only depend on one side, where the support is only on one side, the same trick works. Okay? So now we check the basis case. Now we need to assume that it holds for any box of size lambda n. So a similar trick works for any box, any finite set lambda, for any lambda, when the support of f is the same as the support of g, and it's 1. Okay, so they must be non-decreasing also, but they can only depend on 1 point. We use this. So first, now consider that the FKG inequality holds for any box, for any finite set of size n. Okay, so consider lambda. So consider some x star not inside lambda and take this set here as being lambda prime. So what happens to this expectation value right here? X star beta h omega. Okay. Well, since f and g are local, by the exercise that I just gave you, this will be the same as integrating fg on a smaller box, in this case the box of this box lambda. Okay. Something, this is the function depending on the boundary now, beta h lambda with x prime beta h. So now we are on the nice case, because lambda has only any points and we are assuming that it holds for this, and f and g are non-decreasing. So this is larger than the product of f with some boundary condition here, lambda beta h times g with some boundary condition here, lambda beta h, and you are integrating over this. And remember that I said that the same trick that I did over here works if I considered any probability measure with any box, but the functions having support of only 1 point. So remember, as functions of the boundary conditions, the local Gibbs measures, they depend only of what happens outside the box, the finite set that you are integrating on. So only depends outside lambda. Okay, but since you are also integrating over some larger box, and this is fixed, what happens that this over here will only depend of what's happening between lambda and lambda x star. So these two functions over here, as functions of the boundary, will only depend in what happens in the site x star. So to finish the proof, we need to show that these, as functions of the spin located at x star, they are non-decreasing also. And if they are non-decreasing, then we can apply FKG again and conclude the theorem. So how are we going to do this? Okay. So, what is the Hamiltonian for the system located at lambda? The Hamiltonian at lambda is equal to minus the sum of j x and y, sigma x, sigma y, x and y inside lambda. This is the free part of the Hamiltonian, plus the field, okay, with the magnetic field. And then you have the boundary conditions, and the boundary condition will be sigma x, sigma, x inside lambda, y outside lambda, lambda c, of the boundary condition, of some boundary condition, eta, okay? Eta x, eta y, sorry. So, what happens in this case, integrating this, is that the boundary condition outside this set over here, outside lambda and the point x star, will be omega. So in this case, we will have outside x star, outside lambda together with x star. I know exactly what the boundary condition is in this case, and the boundary condition is omega. And the remaining part will be just a sum over all the sites here in lambda of j x star, the interaction between the spins at x and x star, of sigma x times something, sigma x eta x star, times something that is the boundary condition that is remaining. So I can treat this part as a magnetic field also, because it only depends on one spin, okay? Once I have the boundary condition fixed, this has a similar structure as the magnetic field, okay? So I will introduce for t between -1 and +1, so a real variable in this interval, I will introduce the Hamiltonian t lambda as being the same expression, so the same expression as before, but changing the boundary condition in one side, okay, in this site over here, in the site x star, to a real parameter t. So this will be the yellow part, the yellow balloon, okay, minus jx star times t sigma x inside lambda. So as I told you, you can understand this as if I'm adding some magnetic field. Okay. So what is the strategy? The strategy here is to show that that this function over here, over f lambda beta h t, that is defined as the sum of configurations here of f sigma. Let us fix this as being -1. Okay, so this will be lambda and will be -1. How can I write this? So I write it like this. Okay, this is bad. Okay. So I apologize for this bad notation, but I write like this to denote the configuration that is sigma lambda at lambda. It's omega outside lambda together with x star, and it's -1 in x star. So yeah. I'll write it like this. So I'll write this to denote -1 to denote f calculated at some theta, where theta x is equal to sigma x. If x is inside lambda, it is -1. If x is inside lambda, if x is x star, and is omega x if x is outside lambda, x star. Okay, this is just a notation. And then I will have the Hamiltonian calculated at t lambda beta h over this the partition function, where this partition function is just the sum over all the configurations in lambda of e to the minus to the Hamiltonian that I just introduced. Okay? So define this function over here. And if I show that this function here is non-decreasing, so the strategy is to show that this function over here is non-decreasing. On the interval. So why this solves the problem? Because then I have that f minus 1, okay, and this will correspond to putting the spin here as -1. Beta h is less than f with a +1 beta h. But look at the expression of the function, and you will notice that since this function is also non-decreasing, this is upper bounded. This part is upper bounded by f omega sigma lambda +1. And now this would imply that this measure is, as a function of the boundary condition, is non-decreasing. So if I can show that this is non-decreasing, then it's over. How I will do this? I will just derivative aqui dá, basicamente you just take the derivative and show that is non-negative. So what you do is that you take the derivative of f beta lambda beta t here, and if you take the derivative over here, we already did something related to this. This will give us the sum over x inside lambda f times sigma x lambda beta t here is h minus f t lambda beta h sigma x t lambda beta h. So now remember that this function is also non-decreasing. This is non-decreasing. This is the correlation of two non-decreasing functions. Remember, t can be regarded as a magnetic field. So since I am in a smaller box, I am inside our hypothesis that the FKG holds for any measure here with the size of the finite set equals to n. So I can use the induction hypothesis to deduce that this is positive, and this is a sum of positive things. So the derivative of this is positive. This means that this function is non-decreasing on the interval -1 and +1, and then we finish the proof. Then we finish the proof of the FKG inequality. So a first consequence of this trick is that if I keep getting smaller and smaller boxes, I can deduce the first consequence. The first consequence of this trick is that if I have two boundary conditions here, then I can deduce that f lambda beta h with boundary condition omega will be less than the expectation value of f with boundary condition eta lambda beta h for any f non-decreasing. But see, this order is special because it has a maximum value and a minimum value. And the minimum value is when every spin is -1. So this will always be larger than -1. but it will always be less than the plus boundary condition. Again, for any magnetic field that you want, this will hold. Okay? So nice. So, any questions right now? No? Okay. So, how much time do I have? Okay. So, let us talk about another important consequence of the FKG, and that is how we characterize. How do we characterize the measure? So, you see the FKG in action right now. So, remember, we showed by using the Griffiths inequalities that the thermodynamic limit of the plus boundary condition measure always exists. By the spin flip symmetry that we introduced yesterday, you can also deduce the existence of the thermodynamic limit of the minus boundary condition. But you can also use the FKG to deduce the existence of the thermodynamic limit of the plus boundary condition, and this will be an exercise, so you can check this. Show that for any local function in a sequence lambda n converted to ZD, show that for any local function we have that this limit exists. F lambda n plus beta h for any local function. Okay, this limit will exist and will be equal to the plus boundary condition. This is the plus bound. This is the plus boundary condition Gibbs measure in the thermodynamic limit. Okay, show that this happens. And a hint is try decomposing F as a, okay, no, this will be too easy. So, sorry. So, try to analyze what happens to these correlations. F, okay, times the characteristic of the cylinder, lambda lambda plus. Okay, so this is the configuration that is always plus in the region between lambda n and lambda n minus 1. Sorry, plus 1 and 1. Try to analyze what happens to this case when f is special. So when I say special, I mean non-decreasing. So what happens to these quantities right here? Okay. And the limit, this is the weak convergence of these measures, and this will imply that there exists a measure, a probability measure on the whole configuration space, that the integral of f with respect to this measure is exactly these quantities right here. Okay. And another consequence of fkg. So a similar trick. So continuing the exercise. So what happens to the minus boundary condition measure? What happens to the minus boundary condition measure? So a theorem will be the following. So in the thermodynamic limit, these two are equal. If and only if, now we assume we are in the translation invariant case. Ising. So this in particular means that H will always be the same value, H positive. So the theorem is this. They are equal for any F local. This in particular will imply that the probability measures are equal if and only if if you see what happens to the spin at the site sigma 0, theta H is equal to the spin, to the magnetic, to the expectation value of sigma 0 in both cases. So in this case, by this property right here, this means that whatever way that you take whatever way that you take these limits right here that you get for any measure that you get, every local Gibbs measure will need to, by using this and that property over here, they will need to converge the same value. So there is a unique probability measure. And remember that we saw that when the pressure is differentiable, so there is no first order phase transition, we have that the limit for any boundary conditions of the magnetization density will always be the same limit. So this is connecting what happens to that case when there is no phase transition to a phenomenon of what happens to the Gibbs measures. There is a small difference because there we have the existence of the limit of the magnetization density, and remember the magnetization density is sum over this. Okay, is the expectation value of this magnetization density, and here we are saying that we only need to look what happens to sigma 0. So after I prove this theorem, I will say how the magnetization density relates to these things right here in the limit. But first, let us prove the theorem. So the first implication is it's obvious because sigma 0 is a local function. So if f is equal to sigma 0, so if this equality holds for any f local, then it will hold for this, okay? So the only part that we need to show is this one. So that this equality implies that equality over there. So first, for any a finite subset of CD, notice that the sum of nx in A minus NA is non-decreasing. And we'll remember what nx is. Nx are the occupation variables. The occupation variables. So this is just 1 plus omega x over 2. And NA is just the product of this for any x in A. So this will be non-decreasing. So you can just check it by, you can check directly, right? So since this is non-decreasing, and this inequality holds for every non-decreasing function, this means that the expectation value of this calculated with the minus boundary condition will be less than the expectation value of this calculated, of the same function calculated beta h plus. So what this implies is that, just a second, yeah, this would imply that yeah, if I take the expectation is linear and then I can take to this side, then I get that the difference between the expectation value of NA minus NA beta H, this is less than the sum over X inside A of NX so NX plus minus NX minus beta H beta H. And again, by that inequality over there, I know that this is always larger than 0 because this is the plus boundary condition, this is the minus boundary condition. So what happens? I remember the only thing that I need to analyze is this difference right now. And since I have this expression, I know that this beta H minus NX minus beta H will be equal to the difference between these spins sigma x beta H plus and minus. Okay, so to finish this proposition and to finish the class today, we need to talk about translation invariance now. Because you see, I assumed that they are equal only at 0. But what does this mean for the expectation value of the spin variable at any other site x? So I need to have a way to analyze this thing. If I can show that this condition here implies that this difference is 0, if I know this, if I can show this, then I have that the difference between the expectation value of the occupation variables and A will be less than 0, but they are also non-negative, so this implies that they are equal. And since the local functions are the linear combinations of these variables, this would imply this equality for any plus and minus boundary condition. Okay? So now we need to talk about translation invariance of the system. So I define a translation only on translation invariance. I define it on the level of the coupling constants of the Ising model. But now we define it more generally as an action. So a translation will be the action of ZD on the configuration space by the following map. So for each x, I define these maps theta x of sigma, theta x sigma to sigma, in the following way. If I get a configuration here, sigma, this will have to give me another configuration calculated at some point y, and this will be sigma x plus y. And then you can check that this is indeed an action regarding ZD as an abelian group, because if I translate by x and x prime, this will be the same as I translate by x plus x prime. Okay? And also, if I translate by the site 0, this will give me exactly sigma. So the action of ZD acts on the configuration space and induces an action on the local functions. Okay, by making the composition. So the action is given by the composition of sigma x. Okay? And then you can check that this will be an action on the local function. So what happens when I try to calculate the expectation value regarding the plus boundary condition of f acted by some translation locally? What happens locally? So this will be zeta, the partition function, zeta h, times the sum of sigma inside here, of f composed with sigma x here, e to the minus h plus sigma. Okay, but what is this? The decomposition, we know what is the decomposition. The decomposition will be given by, now remember, we are summing over all the configurations here, because this set right here, this set here, remember, is inside here. Okay. So what is this? This is just f sigma x act on sigma. And then I will do a change of variables, okay? So this will be, I will call it omega. And what happens to the other variables of the system? Well, I know that by this property over here, that if I translate it by x, and then I translate it by minus x, I return to the same point. Then this will give me on the beta h plus the sum over sigma minus x, sigma, theta minus x, theta x, sigma, here, f omega, e minus h plus h, now I have to do the same thing, theta x, sigma. This, again, this is omega. And this will also be omega. Okay? And we can check that. We can check that if sigma minus x here is inside, for a configuration omega, is inside this set over here, this means that omega is inside the image of the action of the configuration space, the image of this translation of the configuration space. But we can write this also as a configuration space. This will be exactly the configuration space in the box exactly translated by x. So this, at the end, will be a sum lambda beta h will be a sum over all the configurations in the translated system, f sigma, the exponential of minus h plus, now beta h, I forgot over here, theta minus x calculated at omega. But again, since the interaction is translation invariant, one can check that for translation invariant interactions, we have that the Hamiltonian here, beta h, calculated at this point, will be just the Hamiltonian in the translation beta calculated at omega. And since a similar trick applies to the partition function, the partition function of the translated system is equal to the non-translated system. So this will imply, finally, that if I act with a translation on the local functions, the expectation value translates the location of where my Gibbs measure lives. And notice that if I consider a sequence converging to ZD this will always hold for every element converging to ZD. The translation also doesn't change the fact that a local function is local. So a function that is translated is still local. So both limits exist because we show that they exist for any sequence converging to ZD. The translation will preserve the property that they are converging to ZD. And by taking the limit, both sides, I finally get that the plus boundary condition measure will be equal to this. When a probability measure on the configuration set satisfies this equation for any translation, then we say that the measure is translation invariant. Okay, the measure is translation invariant. And you see what happens when f is equals to sigma x. Okay, is that the action of the translation will give me sigma x. So the expectation value in sigma 0 is equal to the expectation value at sigma x. So this means that this difference is 0. And then what happens is, yeah, I will erase it. So if the expectation value at the 0 is equal, this means that there is a unique Gibbs measure in the thermodynamic limit. Okay, so we can stop here. E agora eu posso falar mais algumas